Hi everyone, this is lecture video 15 and we will cover inverse trigonometric functions in this lecture. So let's start by looking at this graph. This is y equals sine x graph, and this function is defined, as you can see, for all real numbers, right? You see this is the graph and you will see an image for all the real numbers. That's why the domain of the sine x function is from minus infinity to plus infinity and range is between. So to see what is the range, you will look at all the values, all the images here, all the possible images. And you see that this function sine x takes the values between -1 and 1. That's why this is the range set. And now we will try to understand the inverse of sine x function. To understand that, maybe we can recall something about functions and their inverses. So if the function f is defined from the domain set A to the range set B, then the inverse function is defined from B to A. You see the domain and range set are switched for the inverse function. And to have this inverse function well-defined, to have a well-defined inverse function, the original function has to be one-to-one and onto, okay? This is the crucial restriction for f to have an inverse. Okay, come back to x function, please, a sine x function. And sine x function is obviously not one-to-one. How do you check that? You can do this horizontal line test, because if you draw a horizontal line, you will notice that it will intersect your graph at more than one point, which shows you sine x function is not one-to-one. And we can still talk about its inverse as long as we restrict its domain so that sine x becomes a one-to-one function. So please look at just this portion of the graph, okay? It is from minus pi over 2 to pi over 2. So we are restricting the domain set, which is in fact -1 infinity to plus infinity, minus infinity to plus infinity. This is the original domain now, but we are restricting that domain to minus pi over 2 to pi over 2, just this yellow shaded part. And over this interval, you see that the graph is not, the graph now satisfies being one-to-oneness, because this horizontal line test shows you, now you just intersect your graph. This is the graph, the restricted one, at only one point. That's why after doing this restriction, you can conclude that sine x function, which is this bold blue part, is one-to-one now. It is also an onto function because over this graph, you take all the images in the interval -1 to 1, so it is also onto. That's why from this domain set to this range set, if you restrict your trigonometric function sine x, then you can search for its inverse now. There is no problem about it, the inverse function. And we will be denoting the inverse function with arcsine x. Okay? Arcsine x is the inverse of sine function. And I will prefer using arcsine notation. Your course book uses sine to the power -1x notation. And what is its domain, what's its range? As I recall here, when you come to the inverse function, the range and domain sets are switched. So the domain is this range set here, -1 to 1, and the range of inverse function comes from this set. And after understanding the domain and range of arcsine function, now we can talk about its graph. This is another recall for you. Please remember that the graph of the original function f and the graph of the inverse function are somehow related. How they are related? They are symmetric with respect to y equals x line, okay? Symmetric with respect to y equals x line. Now, by using this fact, you can easily draw the symmetric version of this graph with respect to y equals x. So what do you expect? You will be drawing this graph then. So let's check the domain. Domain is between -1 to 1. Yes, that is just like the desired. And the range is supposed to be from -π/2 to π/2. So you see the range of the arcsine function is -π/2 to π/2. And you will be drawing this graph for the inverse sine function, which is the symmetric version of this part with respect to y equals x line. Okay, so this is the detailed explanation. Why do we have domain and range set like this for arcsine? Why do we draw its graph like this? You can do the similar discussion for arccosine x, for example. And here you see arctangent x. We can discuss on arctangent x as arccosine is so similar to arcsine. Okay, look at the graph of tangent x. So tangent x has this graph. Tangent x is a trigonometric function which is periodic over pi, you know, over all the pi intervals like that. Tangent x function repeats its graph. So it is periodic with period pi. So from these drawings, what do you understand? What is the domain of tangent x function, for example? As you can see, look at the x-axis. Over each x value, you will find an image. I mean, except this -π/2, π/2, and repeating parts. So the domain looks like that. Range, look at the range. Tangent x gets all the value between, you see this part goes till -infinity, this part goes till +infinity. So the range of tangent x function is from -infinity to +infinity. Now, I will also check whether this graph is a one-to-one graph or not. Draw your horizontal line. This is horizontal line test. And you see that this horizontal line intersects your graph more than once, which means that this tangent x is not one-to-one over this domain. But you can restrict the domain so that it becomes one-to-one. Here is our restriction. Instead of taking the whole real line, we will restrict the domain to -π/2 to π/2. So that means that you are just looking this green bold graph now. So over this interval from -π/2 to π/2, your graph is one-to-one now. Okay, this is the restricted domain now. It becomes one-to-one. Then tangent x function has an inverse over this restricted domain because over here it is one-to-one and onto, let's say. So that's why you can talk about arctangent x safely now, and domain of it will be this range set. So you will do this switch. So domain of inverse tangent function is -1 to -infinity to +infinity. Range is like that. How do you draw the graph of it? Of course, you will use this symmetricity information. Now you will try to draw the symmetric of this graph with respect to x-axis, with respect to y equals x line, sorry. It is symmetric with respect to this line. Then you will obtain this graph. We will be using this graph a lot in this course while computing limits or also on other parts. So this is the graph of which function? Arctangent inverse tangent function. So let's check its domain and range information. Its domain is from -infinity to +infinity. You see, domain is all real numbers. Range is from -π/2 to π/2, just like here. Okay, so that's how you analyze inverse trigonometric functions and how you comment on their graphs. Okay, you will find in your lecture notes the inverse trigonometric functions for arcsecant, arccosecant, arccotangent also is given there. Now let's look at this part. here. These are the formal definitions of these inverse trigonometric functions. So this is your course book's notation, but I already emphasized that I will be using this notation for inverse functions. So remember, what is the range of arctangent function? We just talk about it here, right? The range. Range is between minus pi over 2 to pi over 2. So the image of arctangent function is a number over this range. You know, this is the range of arctangent x function. That's why this image is supposed to be a number inside here, such that tangent y is x. Where does this information come from? We can derive it like this. Y equals arctangent x, you know? Then you can apply tangent to both sides. It's kind of taking the tangent of both sides. Then what you obtain? Tangent y on one side and tangent of arctangent x on the right side. Arctangent x. Then, you know, these two are inverse functions to each other. That's why they will kind of neutralize each other. Then this equation becomes just what? X. Okay, so you see, you obtain this result. And similar discussions can be made for arcotangent, arcsecant, arccosecant functions. Maybe I can put here a small recall or warning about the notation. This is the course book's notation for the inverse trigonometric function, and it doesn't mean this, okay? These are not the same. This is the inverse trigonometric function, while this is 1 over the normal original function. Okay, this is inverse function of tangent x, so it is in fact arctangent x. Okay, let's move on. Now we will start computing the numbers coming from the images coming from inverse trigonometric functions. For example, let's look at the first one. Here we are analyzing arctangent of 1 over square root 3. How do we compute this? Okay. Arctangent of 1 over square root 3. This is what we want to find now. What we know about this expression is, okay, arctangent 1 over square root 3. This is a number inside which interval we just talk about it. The result of the arctangent function is a number between minus pi over 2 to pi over 2. So this is a number over this range, 2 plus pi over 2. So that's why we just cancel this part of unit circle. Why do we cancel that part? Because this is the pi over 2 measure and this is minus pi over 2 angle. So we are searching a number over this interval from minus pi over 2 to pi over 2. In fact, you can call this result as an angle theta. So the result of arctangent 1 over square root 3 is kind of asking the angle theta whose tangent is this number, right? So how can I say that? What did I write here? Theta is arctangent 1 over square root 3. Now, take the tangent of both sides. Apply tangent to both sides. So that gives you tangent theta. Tangent and arctangent are inverses each other. That's why you just obtain this. So writing theta equals arctangent 1 over square root 3 means you are searching for an angle theta whose tangent is 1 over square root 3. Now, and one more thing, you know, theta is inside this interval. That's why you are searching theta over here. And look at the tangent of theta. It is a positive number, right? And this is the unit circle. Over this upper part, tangent values are all positive. Over this lower part, okay, let me draw it here again. So we are just interested in this portion of the unit circle where for the upper quarter, tangent values are always positive, and for the lower quarter, tangent values are always negative. That's why now you can cancel one more part, one more portion. Now you are searching for an angle theta. Why I cancel this part? Because we want a positive tangent value. We want tangent to be plus 1 over square root 3. That's why we also cancel this part. Now we are sure that theta lives in this yellow shaded part between 0 and pi over 2. Now you can easily draw this unit a little right triangle there. This is 1, and you want tangent to be 1 over square root 3, right? That's why you will, by the way, this is not a unit circle. You can also use the hypotenuse as to deal with easier real values. So you can create your little rectangle like that. So you see, to have a tangent like this, theta should be a very special angle, which is the value here. It should be pi over 6. So, and that's it. So if this angle becomes pi over 6, which is 30 degrees, then if you choose this angle as pi over 6, which is 30 degrees, then its tangent becomes 1 over square root 3. And how do I know that theta is on this quadrant, on this portion of the circle here? Because I know that tangent theta is plus 1 over square root 3, okay? So now I can write the conclusion over here, and then theta is pi over 6. Okay, let's deal with the second question now. This is the first, this is the second example. Now I am searching for arctangent minus square root 3, okay? Let me rewrite it in my notation, not tangent to the power minus 1, but arctangent minus square root 3, right? Minus square root 3. So the question is in fact like that. Okay, I am searching for an angle theta, arctangent minus square root 3. The result of this, let's say it's an angle theta. So tell me the image interval of arctangent function. It is over here. So, okay, let me write it like this. We are searching for an angle theta, which is the image of arctangent function. Since it is the image, it should be a number over this interval, which is the range of arctangent x function. Okay, now apply tangent to both sides. Then what you obtain, minus square root 3 is tangent theta. So you are searching for an angle theta whose tangent is minus square root 3. Now you will start searching for its region. Okay, as we just discovered, okay, minus pi over 2 to pi over 2. At first, we know theta lies in this over here. And then once we show that its tangent value is negative, then you can say that, over this region, your angle theta lives. How do we know this? Because over here, tangent values are negative, okay? Then you will try to find the correct angle over this region. By correct angle, I mean an angle whose tangent value is minus square root 3. Okay, let's search for it. I think it has to be pi over 3 this time, right? Okay. So let's choose pi over 3, which is 60 degrees. Then what happens? Then you will have some triangle like this. this is 2, this is 1, and this is minus square root 3, if this is the 60 degrees. Then this fits the structure tangent pi over 3 is what? This divided by this, so minus square root 3, everything holds. That's why the angle theta that you are searching for is in fact 60 degrees, which is pi over, it is minus 60 degrees because you are measuring angles normally in the direction of counterclockwise. If you are measuring them in the direction of clockwise, you have to put this negative sign here. So this gives you the result. We were searching for an angle theta, whose tangent value is minus square root 3, and this is that angle. Here it is. Okay, so now I guess we can move on. Let me just also show that tangent values over there is positive. Okay, let's move on. Okay, now we will try to understand how to take the derivatives of inverse trigonometric functions. So maybe I can start by reminding something to you here. So derivative of inverse function. So how do we compute the derivative of the inverse function? We covered this in one of the previous lecture videos. You can compute this without computing the inverse function. In fact, this is related to 1 over the derivative of the original function. Now we will write some points here and here. This is evaluated at the point B, where you have to put here the point A, where A and B are related like this. B is the image of f of A. And from here, you can write A as the pre-image of B, right? So we will be using this fact to prove that the derivative rule for the arcsine function is given like this as a result. Okay, how do we prove that? The derivation of arcsine function is done like this. So you start with sine function. F of x is sine x. And f inverse is arc sine x, and we are searching for what? We are searching for the derivative of this inverse trigonometric function. So what is that? So it corresponds to derivative of this inverse function, and we know how to compute it. Just like here, you need to find 1 over f prime of, instead of A, you can write the pre-image of B, and if you want to insert x here, you can put pre-image of x there. Okay. Okay, then first of all, what is the first derivative of f? Let's compute that. The first derivative function for f is given as cosine x. And now let's try to compute the right-hand side. First derivative function is cosine, and we are putting, or we are evaluating cosine function, which is the first derivative function, at the pre-image function, or at the inverse function, which is arcsine x. So that's why I will put for this one here, arcsine x. Then you need to recall one more thing. Just a second. Okay, let's fix it. This is 1 over f prime, derivative is cosine, and the inverse function is given as arcsine. And what you know about cosine and sine, how they are related. There is this famous trigonometric identity relating sine and cosine, and from here, cosine x can be rewritten as this, sine square x. That's why the denominator here can be written as 1 over, so instead of cosine, I will be using this square root expression, 1 minus sine square x. So sine square, instead of x, what we have? We are evaluating cosine at this point. That's why instead of x, since we have this, I will be inserting arcsine x here. Okay, and then since sine and arcsine are inverse functions, the result is 1 over, they kind of neutralize each other twice. You have square here. So the result is 1 minus square root of 1 minus x squared. So we start with the derivative. We start by searching for the derivative rule of arcsine function. We end up with this just like desired here. So let's put this as a rule. Arcsine derivation is 1 over 1 minus x squared. This is the rule. Let's try to apply it. Okay, let me write it better. Now we will apply this rule over this example. Y is given as, okay, square root of arcsine of ln 3x. So this is a composite function and we want to compute the first derivative of it. As you remember, you need to start with the most outer function, which is the square root function here. How do you derive square root? Okay, quickly I will recall you. Square root function is derived as, this is in fact the power function. You take the power down, you subtract 1 from the power. So it becomes 1 over 2 square root of x. And so 1 over, I am deriving square root now, 2 times itself. So you never touch the insider part, okay? Arcsine ln 3x. And then you should keep multiplying. Maybe I should be writing the next line. So y prime, I am dealing with the square root function first. So the derivative of the square root x is 1 over 2 times itself. 1 over 2 times, I don't do anything about the insider function. Now I keep multiplying with the derivative of the insider function. And about that, I can write you another shortcut. Arc sine not x, but f of x. What if you have this and want to derive? You know the rule. As long as you know the general rule, you can create this one. So by using chain rule, 1 over 1 minus 1 over square root of 1 minus whatever you see inside square, because you have x squared here. And then by chain rule, you keep multiplying with the derivative of the insider function, which is f of x. So to derive arcsine of this thing, you will write 1 over 1 minus whatever you see inside should be squared. Like that. And then you keep moving one step further towards the insider part. Now you will multiply with the derivative of ln 3x. So 1 over 3x times 3 is the derivation of ln 3x function. Okay, that's how we apply the rules. Now let's move on. This time we will try to derive the rule for arctangent x. And let me show you quickly. You start with the function arctangent x. Okay. F of x is tangent x. The inverse function here is arctangent x. And the very same rule we are applying. So we need to find the first derivative function. From here, you can easily find derivative of tangent function is secant square x. That's why you put secant square x for the first derivative function. And inverse function is arctangent x. You write arctangent here. There are also trigonometric identities about tangent and secant. Secant square x is given as secant square x is given as tangent square x plus 1. We will be using this. So secant square of something, okay? So secant square is what? Tangent square of that thing plus 1. Tangent square of the same angle, whatever it is, plus 1. That's why we obtain that arc. Obtain it like this. And then what you see here, you know, tangent and arctangent are inverse functions and they neutralize each other again twice. Be careful. That's why you will have just x twice. That's why this part becomes just x squared. So this gives you the result or the rule for the derivation of arctangent x function. Let me write it here again. Arctangent x derivative. So we are dealing with f of x is tangent x. That's why the inverse function is arctangent x. Okay, let's apply this derivation rule. By the way, I can put a box here because this is the derivation rule for arctangent x. Okay, so this time what you have, y is given as arctangent of something, but 1 over that thing. That's why you have this inverse to the power -1 part. And to take the derivative now, you will deal with first this power function. -1 goes down. You never touch inside by dealing with the most outer function. And then you do what? You need to subtract 1 from the power, okay? So this is how you derivate it. We deal with the power first. And then now I start multiplying with the derivative of the insider part. This is the insider function and we know the rule for it. 1 over 1 plus x squared. So 1 over 1 plus normally x squared for arctangent x, but instead of x here you have what? You have e to the power x. That's why here I will square e to the power minus x like that. And then it's not over yet. Now you move 1 step inside. At the last part, you will multiply with the derivative of the most insider function. So it goes like itself times the derivative of the power, which is -1. So that's your result. Okay, here is the box for you, giving you the derivation rules for all the inverse trigonometric functions. U function here is a function depending on x. In fact, you can think it of like f of x. So arc sine is 1 over 1 minus u squared. If u is a function of x, according to chain rule, you will multiply also for the derivative of u with respect to x, okay? So arc sine, arc cosine. You see, the only difference between the derivation rule for arc cosine and arc sine is this minus sign. And similar thing happens here for arctangent and arc cotangent. 1 over 1 plus u squared times u over ux if u is a function of x. Look at arc cotangent, the same thing with this extra minus sign. And this is the rule for arcsecant. And the same rule applies except this minus sign here for the arc cosecant function. Let me rewrite all those rules once more for you here, and then we will apply these rules. 1 square root of 1 minus x squared. Arc cosine x is the same thing with this extra minus sign. Arctangent x is 1 over 1 plus x squared. Arc cotangent x is the same rule applies for arc cotangent 1 plus x squared with an extra minus sign. Arcsecant x, how do we derivate it? 1 over x squared minus 1. And finally, I can write arc cosecant x. Write the same thing for the rule and then put this extra minus sign. Okay. You can find the rules over here in your lecture notes. Let's start applying them. Okay, if your function is this one, let's find the first derivative of it. Y is given as arcsecant x, arctangent x, and y prime. You deal with the most outer function first, which is ln. How do you derivate ln? It is 1 over whatever you see inside, right? Plus arctangent x. Now, I keep multiplying with the derivative of the insider part, okay? So this part is derivated as, here you see the rule, 1 over x times x squared minus 1, and this part is derivated as 1 over 1 plus x squared, and that's it. Yes, we can solve more questions. For example, this one, y prime is, this is arctangent function, so I am applying the rule for arctangent 1 plus the square of the insider function, whatever it is, you have to square it like this, and then you will multiply the derivative with, we will multiply with the derivative of the insider function. Derivative of x is 1 minus, remember the derivation rule for the square root function, like that, times, now you need to move one step further here. That's why minus 2x comes here. Okay? And then let's also solve this one. Y prime arcsine function. So you start with the derivation of rule of arcsine. 1 minus whatever, the square of whatever you see inside arc, cosine x, square it. And then this should be derivated here. What is the derivation rule for arc cosine? It is the same rule, 1 minus x squared square root. You need to put this extra minus sign there. And this will be the last question that I solve in this video. Arc cosine is minus 1 over 1 minus square of whatever you see here, t squared, times the derivative of the insider function. It is itself times the derivative of the power. So that's it. I stop here. Thank you for your attention.